Assalamualaikum and good evening. Okay, so welcome to EBB 155. Okay, Engineering Materials Introductory Laboratory. My name Dr. Khatijah Aisyah binti Yaakob. I'll be conducting experiment number 2, okay, which is the arrangements of atoms in solid. Okay, so maybe you guys not familiar yet with the arrangements of atom in solid, yeah, because in EBB 113 we not yet touched the topic, or maybe while you are watching this recording you already learn about the crystal structures and the properties. Okay, then it will be easier for you, but for the first two groups maybe it be difficult for you to understand, but it's okay. You can always open up your textbook to do this lab. Okay, what is this lab all about? This lab is all about the arrangements of atom in your solid. Okay, so we only talk about solid for this moment, yeah, because materials is a solid. Okay, so you know that before you have learned about an atoms. If you have one atom, you will have a nucleus, and also you will have electron circling your nucleus, right? But if you have more than one atom, what would be your arrangement of atom inside your solid? Okay, so I'm gonna introduce you some important things that you need to know about the arrangements of atoms in solid. Okay, so in your materials, okay, you will see something like this. Means that you will have a lot of atom. Okay, you not only have one atom, you're gonna have many atom inside your solid. So have you ever think that how does the arrangements of this atom inside your solid, or they just random inside your solid? Okay, so the this guy named Brevis, okay, already classified your atom arrangement in 14 Brevis lattice. Okay, so you can open up any textbook and find out what is the 14 Brevis lattice. Okay, so one of the system in Brevis lattice. Okay, so we have about seven category or seven category. One is cubic, and then you have tetragonals, rhombohedra, hexagonals, orthorhombic, triclinic, and monoclinic. Okay, so for I'll give you examples. So actually beside me is a lot of crystal system. Okay, so the simplest one is the cubic system. Okay, okay. So in the cubic system, it's very easy. You have a square and then atom all at the corners. Okay. Okay, so this is the easiest or the simplest system of the Brevis lattice. Okay, so this is a cubic. So if you see the cubic, okay, cubic is a cube, have all side the same length. Okay, all the length is the same length. Okay, so at each corners of your cubic will have an atom. Okay, so they're going to have 8 atoms all together inside your cubic. So under the cubic system, you not only have a simple cubic, okay, not only have simple cubic like this, but you're also going to have a body center cubic. Okay, what is the difference between these two? Okay, you can see this cubic, simple cubic, is only have 8 atoms. Whereas for the body center cubic, you're going to have 9 atoms. You have extra atom in the middle. So that's why we call it as a body center cubic. Okay, and we also have another one more unit cell inside the cubic system, which is the face center cubic. So again, I want to show you what is the difference between simple cubic and face center cubic. So for the face center cubic, you're going to have more atom than the body center cubic and also simple cubic. So you can see all the atoms at the surface. So this is your surface of your cube. Okay, all the atom, 8 atom at the corner. Okay, and you're going to have extra atom on the surface. Okay, so you're going to have 6 more extra atom because you have 6 surface of a cubic. Okay, that is for cubic system. Okay, then we also have a tetragonal system. Okay, so this is a tetragonal. Okay, so this is a unit cell for tetragonal. Okay, so in the tetragonals, okay, it's the same as cubic. Okay, simple like cubic, but only the length of the z-axis, okay, not the same as the x and y-axis. So it's more like, the shape is more like rectangular shape. For the cube, it's a square shape. Okay, so for this system, tetragonal system, you also have another unit cell. This is a simple tetragonals. So you're going to have another unit cell, which is, it has 1 atom in the middle. Okay, it also have a rectangular shape, but with an extra atom in the middle. Okay, that's for tetragonals. Then we're going to have a rhombohedra. So rhombohedra definitely different. Okay, if you can see rhombohedra, okay, it's different because it's a parallelograms. Okay, so the angle between the angles between the x-axis and z-axis is different. It's no longer 90 degrees like in simple cubic. Okay. So the angles would be, you can check this, what is the angle for tetragonal, for the rhombohedra. Okay, so I don't have it here. The tetragonals, rhombohedra, tetragonals, cubic, trigonal. Sometimes they call it as a trigonals. This rhombohedra. So the trigonals. Oh no. Another mistake. Not this one. Hexagonal. I have no information on this. Okay. So and then we have hexagonal structure in the Brevis conventional unit cell. Okay. So this is hexagonal. Hexagonal also only have 1 unit cell in its category. So you can see that you have 6, 1, 2, 3, 4, 5, 6, 7 atom on the surface, 3 atom in the middles, and another 7 more atom on the base. Okay. Then you're going to have a orthorhombic. Orthorhombic is it has more unit cell in the group. Okay, so this is orthorhombic. Okay, so again you can see the angles between x z-axis, y-axis 90 degrees. Okay, between the z-axis and y-axis also 90 degrees, but only the length, x-axis, y-axis, x-axis, y-axis, and also z-axis is not the same. Okay, under this category system, you're going to have a 4 unit cell. Okay, you're going to have this kind, this type. Okay, so you have 1 atom at the surface above and 1 atom at the surface below. Okay, but no atom on the other surface, only on the top and the bottom. Okay, and also you're going to have atom in the middles. Okay, so this is orthorhombic. Okay, there is 3 and atoms or atom on the surface. Okay. And the last one is triclinic structure, triclinic unit cell. Okay. So the angle between x-axis, y-axis, z-axis is not the same as in cubic or your trigonal. Okay. Okay. So this is just to give you some introduction to the 14 brevis lattice. So the arrangements of atom inside the material is actually not restricted to this 14. We have more, but only brevis has make a classification into this 14. Okay, so you can find others as well later on. Okay, so let us go. That is my introduction, just to let you know that atom is actually has its own arrangement inside your materials. Okay, so okay, so back to our lab manuals. If you can see, if you have your lab manuals with you, okay, you can lab manuals. Inside this experiment 2, we're gonna have 2 parts. We have part A, okay, and also part B. Part B, let me see my manuals. Okay, part A and part B. Okay, okay. So the part A would be the arrangements of atom in solid. Part A number 1. Okay, you also will learn about the arrangements of atom, arrangements of ion in solid. Okay, so arrangements of atoms in solid means if you have only one element. But if you have 2 elements, so it's going to be arrangements of ions in solid. Okay, for part B, you will learn, you have to do the Miller crystal lattice and structure. Okay, so okay, shall we continue? Okay, so experiment 2, part A. Number 1, the arrangements of atom in solid. Okay, so the objective of this experiment, okay, so to make you understand the arrangements of atom or ion in 3-dimensional model, which is otherwise it is difficult to visualize theoretically or by drawing, and using a graphical program called CrystalMaker to view and also to manipulate your models of your crystal on the computer. So what does it mean? Okay, if you only draw your crystal structure on the paper 2-dimensional, it's difficult for you to view much more closer. Okay, as compared to if you're making a 3D models. Okay, so in this lab you are making models for your crystal structure. Okay, so it's easy for you to understand more, okay, and easy for you to visualize the models, okay, instead of only drawing it 2-dimensional. Okay, so inside this lab also, if you have a face-to-face session, you also will have you also will use the CrystalMaker software to draw your crystal structure. But because you are away, so you maybe next time when you are in the campus, I can show you how to use a CrystalMaker software to draw your crystal structure. Okay, so the introductions or theory, a little bit of theory for this lab. Yeah, I might be not follow the, you can read through, but I will do my own introduction. Okay, so for examples, if you have this material again, I take this structure. Okay, so this is a crystal lattice. Okay, so your atom inside your material, they are all arranged. Okay, like this. This is only one example. I use this for examples. Okay, so they arrange. Okay, so this is, we call it a crystal lattice or crystal structure. Inside this crystal structure, there would be one, the smallest, they call it, okay, the smallest entity in the crystal lattice. So, you can see one pattern inside here. Okay, the smallest pattern inside the crystal lattice. Okay, we call it as a unit cell. Okay, okay. So, okay, that is a definition of your unit cell. Or maybe I just read through the introduction. Crystal lattice consists of repeating patterns of its component in 3 dimensionals. Crystal lattice represent the entire crystals by stacking together the smallest identical unit, which is called unit cell, and form the crystal. So actually your crystal, this crystal, it make off with a repeating unit cell. So you have like this unit cell, okay, so it repeating many times inside your material. So then you have your crystal structure. Okay, okay. So that we call it as a crystal structure. Crystal structure is actually the repeating unit of your unit cell. Unit cell is actually the smallest entity inside your crystal structure. Okay, so examples of this unit cell, okay, such as simple cubic, body center cubic, face center cubic, and hexagonal closed pack. So not only limited to these 4, okay, you also have another more. You also have, like I tell you just now, okay, so the tetrahedrals, you have the monoclinics, triclinics, okay, then not also limited to these 14, you also have more structure, okay. Okay, so but in this lab, you're going to use a polystyrene ball to make your own model. So we only ask you to make for simple cubic, body center cubic, face center cubic, and also for hexagonal closed pack. Okay, so inside this, you're going to make your 3D models using a polystyrene ball. Okay, so the material that for this lab, you will learn about 3 cubic system. Okay, so you will learn about this simple cubic. Okay, body centered cubic, where you have one atom at the center, and you also will learn, or you will analyze more details on this cubic. So you will have a face-centered cubic system. So for face-centered cubic system, that like I already mentioned just now, you have atom at all the 6 surface of your cubic. Okay. So I also have made models, okay, for you guys to see. So this is the model using a ping pong ball, okay, of face center cubic or FCC, okay, ball. Okay, so the material that you can read through the materials and also experiment procedure. So to build up a crystal structure, so to build up a unit cell, 2.4.1. Okay, so the atom in crystal occur in plane. Okay, so your atom will arrange in a plane. Okay, okay. Sometimes a crystal will cleave readily at such plane. Let us begin with 2-dimensional crystal in which all the atom lies in array in a single plane. Okay. So what you need to do for the first one, you need to draw an array of point, okay, and then identify three possible way of a single plane or identified three unit cells from the TOS arrangement. Okay, so for the 2.4 building of crystal structure, 2.41 unit cell. So the atoms in crystal occurs in plane. Okay, sometimes a crystal will cleave readily at such plane. Let us begin with two-dimensional crystal in which all the atom lies in an array in a single plane. So if you have an array of atoms like this, what I already wrote down on the whiteboard. So I want you to identify three smallest unit cell inside here, or three patterns of unit cell inside this arrays of atom. So one of examples I can give you that you can make a square. Okay, so you can find one small unit cell inside this arrangement. One is square. Okay, so we call this a unit cell. So another you need to find out or draw inside. Okay. So, 2.4.2 model building of closest packing structure. Okay, so place 19 white balls into the space surrounded by the plastic stripes. So this is the plastic stripe. Okay, this is the white ball. We have 19 balls here. You will need to arrange the balls in such of that hexagonal shape. Okay, which you have three balls at the side. Okay, so this arrangement is the closest packing possible arrangement. Okay, so inside this arrangement, if you see closely, okay, you can see there is actually okay, so you can see directly into the closed pack layer from above. You will be able to see a triangular shape between the sphere. Okay, this is a triangular shape between the sphere. Okay, so there is two type of triangular shape. Maybe this one is not so clear. Okay, I'll show you. So this will be representing the ball in the pentagon. Okay, so because it's difficult to see from the top, so I make this arrangement. Okay, so if you see here, you can see there is two types of void in this arrangement. Okay, you can see that the void shape is triangle. Okay, both are triangles, but one triangle that is pointing down. Okay, the peak is pointing down. Another one, the peak is pointing up. Okay, so these two is actually different. Okay, so I already have another one more models for you to see. Okay, so I already labels. Okay, so the void that pointing down, okay, I put the red beads. The void that pointing up, I put the blue beads. Okay, okay. So in your lab manual, you are asked to take to give name for the void that pointing down, to give name as D. Okay, and the void pointing up to give name as U. Okay, so then you are advised to you are asked to take only three atoms. Okay, so I have this model for you. These three atoms. Okay, so then you have one void. Okay, on top of these three atoms, you put another atom on top. So your void here or your holes here will be named as a tetrahedral holes. Okay, so these four atoms will form a tetrahedral holes in the middle here. Okay, this is a tetrahedral holes. So why that we call it as a tetrahedral? Because these four atoms have have 4 surface. Okay, 1, 2, 3, and 4. It is like a tetrahedral shape. So that's why the void that form with these 4 atoms, we call it as a tetrahedral void. Okay, so not only you have tetrahedral void, there is another void. One more is made from 6 atoms. Okay, so octahedral. Okay, you will have 4 atoms at the as a base, 1 atom at the top, and another 1 atom on the bottom, top and bottom. So here then you will form a octahedral holes. Okay, octahedral holes. Okay, why we call this octahedral holes? Because it has 8, 1, 2, 3, 4, below another 4 surface. This much easy, but this is white color, it's difficult to see. This is octahedral. Okay, so in the middle here there is an empty space, we call it a octahedral holes. Okay, so octahedral holes formed by 6 atoms. Okay, but these 6 atoms have 8 surface. 1, 2, 3, 4 at the top, and another 4 more surface at the bottom. That's why we call it the octahedral holes. Okay, so inside the cubic system, you will have 2 types of hole: tetrahedral and octahedral. Okay, in your lab manual later on, you need to form this octahedral and tetrahedral holes. Okay. Okay, then we continue on how to make the hexagonal closed pack and also face center cubic. How to build up these 2 structure. Okay, so in this cubic system, simple cubic is the most not so packed structure. Okay, but the face center cubic, face center cubic is the most packing structure. Okay, so how that this structure can form. Okay, so we can form by, okay, just now I show you, okay, the arrangements of atom, okay, in one layer. This is first layer, so you have a void. Okay, so you have void pointing down, void pointing up. So the void pointing up and pointing down, so I put colors, I put the beads. Okay, so to make it look different. Okay, so the red color is the void pointing down, and the blue beads is the void pointing up. Okay, so this would be your first layer. Okay, so if you stack another layer on top of this layer. Okay, for example, you stack another layer on top of your red beads. Okay, on top of your, the red beads. Okay, on top of your red beads. Okay, on top of your red bead. So that is your red bead. Okay, so you put another layer on top of your red bead, so you can still see red beads. You can still see the blue bead underneath. Okay, underneath this. I hope that you can view, you can see. Okay, so now we have a layer. The first layer we call it as a layer number A, the white ball. Okay, so the orange ball, okay, is a layer, second layer, layer B. So A, B. Okay, so these two atoms is arranged in a different position. Okay, between the layer A and the layer B, because the layer B, the atom is positioned on top of your blue beads, on top of your red beads. Okay. Okay. So then, if you see from top, you still can see the blue beads. Okay. So you can still see the blue beads. Okay. So means that you can stack another layer on top of your blue beads. Okay. This is, we call it layer number 3, which is the layer C. So you have 3 different layers, okay, or atom arrangement, where you have layer A, B, and C. Okay. So this arrangement will give you the FCC structure. Okay, will give you the the face center cubic structure. So means that if you're stacking, okay, you have this void, okay, the void pointing up, void pointing down, and if you layer out another layer of atom, okay, position on top of your red beads, then you're going to have another different layer arrangement, which is, we call it the B layer. Okay, and then if you put another layer on top of your B layer, okay, on the blue beads now, okay, so you will form the third layer, which is, we call it as a C layer. So repeating this layer throughout your materials, then you will form a FCC structure. Okay, the same also goes for if you want to make the HCP structure, hexagonal closed pack unit cell. Okay, so again you're going to have this arrangement of atoms. Okay, so for the HCP structure, first you will stack another layer of atom on top of the red beads, where you have layer A is your white atoms. So nampak ni. Okay, layer A is your white atoms, white ping pong ball, and then layer B is the orange ball that's stacking on top of the red atoms. Okay, so you still can, if you see, you still can see the blue beads. Okay, the blue beads, you still can see the blue beads. Okay, okay, but this time you are not stacking on top of the blue beads, but you stacking back again on top of your white atoms, the same position as your first layer. Okay, and this is a bit difficult. Red and okay, this arrangement. So you have layer A, layer B, back to layer A. Okay, so repeatedly, continuously, have this repeating AB structure, then you will get your hexagonal closed pack like this. Okay, so for the hexagonal closed pack structure, so you have 7 atoms at the top, 3 atoms in the middle, and another 7 atoms at the bottom. Okay, so this is your hexagonal closed pack. So the first layer, layer A, layer B, and again layer A and B, and repeat it throughout the materials. So these two structure is actually the most dense structure in the unit set, the 14 Brevis lattice. Okay, so but it is not 100% occupied by the atom. Okay, so it still have some empty space inside. Okay, you can see that beads representing the holes inside. Okay, later on inside your lab manuals, you need to identify how many tetrahedral site inside your FCC and how many octahedral site inside your FCC. And also you need to do it for hexagonal closed pack. You need to identify how many tetrahedra and how many octahedra inside your HCP structure. Okay, so okay, hi student. Again, we shall continue with part 2, arrangements of ion in solid. Okay, so the previous experiment or the previous explanation is more on the atom. Okay, atom arrangements of atom in solid, meaning that you only have one atom in your crystal structure or in your unit cell. But what happen if you have more than one? So how are you going to arrange your atom if you have more than, or if you have two elements or two types of atom? Okay, so we call this arrangements of ion in solid, because normally you will form an ion and cation. Okay, so how you going to arrange this? Okay, so for the ion, normally you will have cation and anion, and your anion normally is much bigger than your cation. Okay, so this is octahedra, where you have 4 atoms as a base. Okay, 1 atom at the top and 1 atom at the bottom. So in the middle is the octahedral site. So if you have smaller cation which can squeeze inside these interstitials, so then the cation will sit in the octahedral interstitial site. And last one, we have the tetrahedral site, where the base is 4 atoms and 1 atom at the adjacent or on top. So form a tetrahedral site. So in the middle here is your tetrahedral interstitial or holes. Okay, if you have smaller cation, it will sit there. Okay, so if I give you a material, how then to know, how you can identify whether it in the interstitial, in the cubic, interstitial cubic, or octahedral or tetragonal? Okay, so please refer to table 2.1. Okay, so from that table you can identify the interstitial site and also the structures of your materials. Okay, would be following this table. Okay, so how do you gonna do it? You just take the radius of your cation, the smaller ion, over the radius of a bigger anion. Okay, so if the ratio is in the range of 0.225 to 0.414, means that it means that your cation is will be sitting in your tetrahedral site, okay, or holes. Okay, and if your radius ratio is in between 0.414, so it will fall up to 0.732, so your interstitial site would be octahedra. And if your ratio cation to cation radius to anion radius in between 0.732 to 100, it will be a cubic. But for cubic, they will have 2 cation and anion ratio. If the cation to anion ratio is 1:1, so it will fall into the cesium chloride crystal lattice. Okay, or lattice structure. And if it is in the ratio of 1:2, it will fall into fluoride lattice structure. Okay, so if you turn to the page 13, Okay, we have a question over there for you to answer. Okay, so because you don't have this model, maybe the A you can get information or diagram from the internet and can answer all the question below. Okay. Okay, so for the question for discussion, the last part, which is you need to do a calculation. You need to find out what is the interstitial side, the lattice structure, and also arrangements of ion in the compound given: thorium oxide, calcium fluoride, cesium chloride, magnesium oxide, and also natrium chloride. So you need to find out what is the arrangements of ion, what is the arrangements of cation, what is the lattice structure, okay, and give all this, calculate all this and put it all the information inside a table. Make or tabulate a table for this part. Okay, so page 14, okay, is an ionic radius. Okay, so it's an ion and cation radius are given to you. Okay, so all the cation or an ion value is given in the bracket. Okay, the unit is picometer PM. Okay, so for part B, I'll be continue later.